Let's do a sound check. Can you hear me? Yes? Loud and clear? Okay, good. Good morning. Welcome to, this is 1101s, right? Okay, good. All right. My name is Terence Sim. I'm guest lecturing for this week because Ben Leong is away. He told you, right? Okay. Okay, so, because I see some shocked faces. Okay, so we should get started, no? Yes? All right. Is this the regular class size? It is. Should I dim the light? Should I? You prefer this or you prefer this? This is better. Okay, this is better. Yeah, you don't have to see me. Just look at the screen. Yeah, 43 people, right? So that's kind of... you realize I can see your photos here. I mean, so can Ben, right? Lecturer's privilege, right? The photos are what? Well, it depends on what you submitted, right? Yeah. You can always update it, right? Are you ashamed of your own photo? I see. Right, so you know, some photographs have a greenish tinge, for instance, the one here. I don't know why. Maybe it's the camera or the lighting or... Don't tell me your skin color looks like that. It'd be kind of sad. Anyway, so 43 people, that's kind of about right. Okay, so let's get started. I'm going to be guest lecturing, as I said, for today and Friday's class, just for the lectures, okay? Recitations and all that go on as per normal with your regular instructors, okay? So, yeah, today's lecture will be the last one on scheme. Yay, so is that joy or reluctance or... Huh? On Friday we will start Java, okay? Now I know some of you already know Java, right? Is that right? Okay, but we're going to... You know, now that you know scheme, you can appreciate Java even better. Okay? So that's kind of the flavor we're doing. I used to teach this class several years ago. And Ben has been taking over for the last 6 years. But I used to teach it. Okay? So I hope I can still remember. If I'm wrong, you tell me if I go wrong, okay? All right, relax. Okay, so today I'm going to talk to you about lazy evaluation and streams. I'm going to tell you that laziness is a good thing. Now, before I get sued or whatever and say, oh, this lecturer tells me to be lazy. Laziness as a programming concept is a good thing. Or rather, it can be good, it can be useful. Okay, I'm not saying that you should live your life in a lazy fashion. That's not what at all I'm saying. So I have that caveat first, okay? So, but as a programming concept, you will see today that really, really it gives you a new kind of power that you never thought was possible. Okay? And it's, like with the rest of the scheme class, be prepared to have your minds blown away. Is that a fair statement? How's the class been so far? How's the material been? Yeah, fun, right? Blows your minds away. Even the homework's even worse, right? I know Ben, right? He takes delight in crafting very good homework, problem assignments that really stretch you. Okay? But it's part of the game. Okay? When I took the course, I took this class over 20 years ago. I went through the same thing. Okay? That explains my lack of hair. I mean, it's kind of the frustration and the late nights. Okay? So I know some of you also look like you're like me already. So. No, but, okay, so we're going to have some fun. It most likely will be a short lecture today. But we can go on for as long as you want. Please feel free to interact and ask questions. Okay, so let's get started. Today's agenda, you can read for yourself. All right. So, so far in scheme, you've been doing what is called eager evaluation, right? And the idea is written there, right? When you call a scheme procedure, it immediately does what it's supposed to do, right? And then if you're the caller, you have to wait for that result to come back before you can continue. Am I right? That's how procedures call another procedure. Okay? So that's called eager evaluation. In other words, the moment the procedure is called, execution takes place, and whatever results there is done. Okay? Today we're going to say, well, maybe let's relax that. Okay? We're going to do something called lazy evaluation. The idea of lazy evaluation, okay, maybe I'll illustrate this. Eager versus. So suppose I ask you, can you please buy me a coffee, right? Let's say. And eager evaluation is when you immediately run off and come back and buy me a cup of coffee. Thank you very much, right? Okay. Lazy evaluation is like, I say, can you buy me a cup of coffee? And immediately, you say, done. Okay? You don't even leave your chair, you don't leave the room, you don't do anything. You just say, done. Then I'm like, so where's my coffee? Right? But the beauty of it is that the moment I take, this is tea, by the way, not coffee, but the moment I want to drink, let's say I raise an imaginary cup, then magically, he runs off by and then gives me a cup of coffee at the moment when I want to drink it. That's the difference between lazy and eager. Okay, so in lazy evaluation, you sort of say, yeah, done. There's no waiting time, right? You tell me to do something, you call a procedure, the procedure returns immediately, pretty much. There's little computation to be done. Okay, and then when you finally want the actual result, or whatever that might be, that's when the evaluation takes place. Now, you've seen an example of that. Can you recall? Okay, maybe it's not so obvious. Remember, did you do that make red, print red, the rational? Yeah, you did that, huh? Rational, yeah, okay. Do you remember the choices we made when we tried to reduce to lowest terms? Do you remember that? You know, a rational number has a numerator and denominator, right? And then we said, okay, numerator is a fraction. It may not be reduced to lowest terms, right? And then the question was, well, that's a nice thing to do, but the question is, when do you do it? And you had a couple of choices. Do you recall? What were the choices? Bingo. Thank you. Do you remember that? Huh? You can reduce to lowest terms at the point of creation of that new rational number. That's one choice. The other choice is when you print it, only when you need to display it. There was a third choice, do you remember? Not quite. You talked about creation and printing, display. You mean numerator, denominator? Yeah. Okay, same idea. You need that for, yeah. Complex numbers don't have reduction to lowest terms. But that's fine. That's fine. That's why you need coffee. Can you ask him to buy for you? Just kidding. So the three choices were during creation of the rational number, during printing of the rational number. The third choice was when someone wants to access the numerator and the denominator, right? When somebody says, give me the numerator of this rational number. That's when you calculate and reduce it to lowest terms. Okay, remember that. Now, there you have it. That was the first instance of lazy evaluation. You may not have noticed it. When you reduce lowest term at the creation, you're doing eager evaluation. You're doing all the work you can right up front. But when you delay your reduction until printing time, you're doing what's called lazy evaluation. Okay? You're not doing any work until it's absolutely required, right? Now, many of us, when I was your age, it was like that, right? Clean your room, my mom says. Yeah, done, mom. Done. Until she bursts open the door. Oh, yeah. Okay? So that's lazy evaluation. We all are familiar with this strategy, right? So we're going to do it in terms of programming, okay? Now, in order to do that, you can imagine that we need a new special form. Okay? It's written there. Delay. Delay is a special form and then a primitive called force. This is not Star Wars. But it just happens the name got stuck. Okay, this is not Star Wars. Okay, so the idea of delay is you delay an expression. The expression is actually not evaluated. It's somehow wrapped up and frozen. Okay, in scheme like there are various terminologies for this. Schemes calls it a promise. It's like an IOU, right? I promise you I will do it in the future. Okay? So that's called a promise. Other people call it thunk. 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 Okay? Or you freeze the thunk, and then when you want to use it, you thaw it, as if it was a block of ice. Alright? So here we delay and we force it. Okay? Force is the so hang on, just the second statement, right? So delay has the effect of decoupling the time of object creation and object until the usage of the object. Okay? Right? And then force, okay, so here's the case. So this produces a new computation object called a promise. The expression, nothing is done to it. It's sort of just wrapped up as is. As is. Nothing is evaluated at all. So I'll show you an example, okay? And then force takes the promise and forces it. In other words, says, do it now. Do the evaluation right now. Okay? Okay, so we're going to see an actual... Okay, so Ben put the order differently. But here, so let's think about how you might implement this. Okay? So one way is to do this, right? Delay expression is syntactic sugar for that. For the lambda, it's a procedure with no arguments, with the body, with the expression being the body. You have seen lambda expressions like that, right? What is the effect of that? You create a lambda object, right? A procedure object. Is the expression evaluated at this point? No, right? But rather you wrap it in this lambda thing. Finally, when you call this lambda, you invoke the procedure, then and only then is the expression evaluated. Okay? So it can be delay can be implemented in terms of lambda, something you're already familiar with. Okay? This doesn't work. Why? Yep. Exactly. Okay? This is a regular procedure. It's not a special form. And therefore, when you call delay like that, the EXP will, in fact, get evaluated right there and then, which is not what we want, right? Okay? So therefore, it shows you that delay has to be a special form. Okay? So syntactic sugar just means it is a shorthand. Huh? Okay? You know what that means. All right. So, whereas force can be a regular procedure. Okay? All right. No surprise there. Okay, so here's an example. Define y to be delay of plus 10x. And then y, when you type y, scheme interpreter tells you, it tells you something called a promise. It's a new type of object. Okay? Internally, we don't know how the scheme interpreter does it. I'm showing you that using procedures is one way, but that may not be the way scheme actually does it, right? But in any case, it shows you promise. Okay? So, 2 weeks later, now you define x5. You see, without the delay here, if you just said define y plus 10x, at that moment, if x is not defined, you're going to get an error, right? Unidentified, identifier, whatever error message you get, right? But with the delay, you don't get an error because you get a promise, an IOU. Okay? So now when you define x5, and then you say force y, you get 15. See what's happening? Okay? It need not be 2 weeks later, it can be 2 years later, right? Okay? That's the idea. You can therefore decouple creation of the object from the actual usage of the object. Powerful concept. Powerful concept. Okay? Now, it doesn't look very exciting, but when you combine it with streams, then be prepared to have your mind blown away. Okay? So we'll show you. Okay, so take a look at this procedure. What does it do? Anyone? Yes. Yeah, essentially. Right? It checks if proc, the PROC, the argument there, which is the procedure, it checks if it's already been run before. Of course, the first time you do this, it's not run, right? Then if it's not run and you call it, then it will run. And remember the result. That's it. The key point is, this is a form of memoization. Have you seen memoization? Yeah, okay, so this is memoization for you. Okay? All right. Very good. So it remembers the result for procedure, right? So that's one way to optimize. You see, when you delay an object, you delay an expression, and say 2 weeks later you force it, that's when the computation takes place, and that could take a long time, right, depending on the complexity of that expression. Okay? So now that you have the result, suppose you delay it one more time. Force it a second time. Do you want to go and redo the calculation again? You could. I'm not saying you couldn't, you could. Or you could cache it, right? You could memorize it. So that saves you a little bit of time later on. Okay? So remember, memoizing a delayed object, a promise, is actually optional. It's a design choice. Okay? The scheme we'll see later whether the Dr. Racket does it. Okay? All right. So again, we can optimize delay as this thing. Delay is syntactic sugar for this thing with the memo prop. Okay? So this is how you would implement delay with a little bit of efficiency thrown in, right? Okay? Okay. This works for only expressions with no side effects. Huh? Why? Right. Did you hear that? Okay? Because once you memorize it, the next time you call it again, it's just going to return you the result without actually evaluating the expression. So if the expression was, say, print something, display something, the second time around it's not going to happen. Clear? Okay? All right. So another one. Can you tell me what this one does? Can someone else try? Let's have somebody from this side. I feel like a game show host, no? Ready, chill. This side. Anybody? No, sum of prime numbers, yeah? Between A and B, right? Sum of prime numbers between A and B. Very good. You guys are pretty good at... You're all ready for the final exam. I will tell Ben that. No, kidding. Great. You guys are becoming very good at reading programs, which is the goal of this course. Okay? To be able to read. Alright? So it's actually summing primes. This is the same procedure, but just change the name to be a bit more like sum primes. Okay, so it computes the sum of all the prime numbers in the interval A, B. Alright? So, now, you actually saw this in your list processing, right? Somewhere back in chapter 2 of your book. Do you remember that signal processing approach? Yeah? You did something like this, right? Or at least you know what this means, huh? This style, where you first enumerate interval, this thing right at the bottom here. Right? You know what that does, right? It lists all integers from A to B. And then if that gets passed to a filter with that predicate prime, so what's that going to do? It returns for you only the prime numbers. Filter predicate returns the list of elements where the predicate evaluates to true. So you only retain the prime numbers. Okay? And then finally, you pass that to accumulate. And you know what that does, right? Accumulate with operator plus initial value 0, that performs a sum. Okay? Right. So, of course this works, right? Okay? Alright? Now, consider this, okay? Enumerate interval 10,000 to whatever that number is. I have trouble finding 1 million. 10,000 to 1 million. Okay, filter prime, and then car encoder. This, yeah, you want the second prime number in that interval. Okay, obviously, the second smallest prime number in that range. Okay? So you will get the result. The question is, how efficient is this? Kind of dumb, right, if you think about it. I mean, you just want the second prime, but you went all the way to list everything from, 10,000 to 1 million, which is a lot. And then you filter, all the primes. Testing prime takes a bit of time as well. And then finally, you only take the second one. It's like, why go through all the effort? Why go through all the effort? Okay. If you knew that you were only going to get the second prime, if you knew, then of course you can say, well, let's not do so much work, right? The problem is you do not know. Imagine you were enumerate interval. Imagine you were enumerate interval, or you were this filter. Either one, doesn't matter. You will not know to what use your result will be put to. You will not know how your result will be further used. Am I right? So you have no way of knowing that there was a coder and a car waiting for me. Okay? So therein lies the problem. So the way to go about this is to actually be smart and use lazy evaluation. I don't know, so imagine you are enumerate interval. You're going to say, look, this looks like a heck of a lot of work, right? And I don't know subsequent uses of the result I'm going to give. So instead of doing the eager evaluation, I'm just going to do lazy evaluation. I'm just going to produce one result, okay, just to be safe. Produce one result, and I delay everything else. Okay? And then only when whoever else needs the second result, the third result, then I produce more. I produce the result, compute on the fly, as it were. Okay? So that's kind of where we're heading. Okay? All right. Define primes recursively. How do you define primes? Okay, never mind. We'll come to that later. Okay? don't know why he threw the exercise here. These slides are from Ben. I try not to reorder them too much. All right. So let's look at this. Like I said, delay by itself is not very interesting, but now let's use delay and package it to create a new data structure called a stream. Okay? So as before, you have a constructor and two accessors, constream, stream car, and stream coder. Okay? So constream is equivalent to const A delay B. Again, constream has to be a special form, yeah? Agreed? Okay? Constream cannot be a procedure because otherwise B would be evaluated, which is not what we want. We want to delay B. Clear? So constream is a special form. Syntactic sugar for const A delay B. And then the selector stream car and stream coder. Stream car is the regular car, just returns the first element of that pair. Stream coder forces the evaluation. You can see here. Stream coder, the bottom one. Stream coder returns the coder, but because that was delayed, we're now going to force it. Clear? Okay? So conceptually, it is no different from your const car coder that you saw earlier. You manipulate, you can const car coder, the same thing, right? You can check for null, you can do your map, you can do your filter, you can do all of that good stuff that you saw in chapter 2. Okay? The only twist now is that hidden away from your eyes is this delaying mechanism. Okay? But that makes a big world of difference, as you can see later on. Okay? So conceptually, it's everything you've seen before. Okay? So from here, we can define stream ref as like list ref. Okay? Same as before. I won't go through this because it's similar to what you've seen before. Okay? Stream ref selects the nth element from the stream. Okay? Remember, nth element but you start counting from 0. This is what differentiates computer science people from other people. Other people start counting from 1. Computer science people start counting from 0. Clever. Good job. So we know you are computer science trained when you start counting from 0. Okay? No, seriously, comp science people start counting from 0. Alright? So you see an example of that. You can define your stream map like your map. Okay? Same thing. Everything is just defined in terms of const, car, and coder. No difference. You do not need to delay or force anything here. Abstraction barrier. Remember that? Abstraction barrier. Okay, the delaying and forcing is done by constream and stream coder. You are now using these, and therefore you don't have to worry about those things, right? Abstraction barrier. Okay, so if you look at this definition, it's exactly the same as when you're handling regular lists. Okay? All right. Filter, same thing. Take a quick look. It looks exactly the same. You wouldn't know there is a difference. Yep. For constream, yes, correct. The way we have defined constream. List stream, you can define it. No, there isn't. I mean, it's not a primitive. That's what I mean. Yeah, it's not primitive. Which expression, A or B? Yeah, B. When you say constreams A, B, if your B, no, if your B is whatever that whatever is frozen first.
But I mean, it would look like a list if the B was some recursive const.
Yeah, I mean, you can think of it that way, right? But try to think of streams as a new data type, data object. Okay, conceptually the same as lists. Conceptually. Yeah, well, the equivalent is called the stream noun, or the empty stream. Can you see somewhere there? In the first con clause. That serves the function as a noun. Not in Dr. Racket. Not in Dr. Racket. So in Dr. Racket, I think if you look at the scheme code, which I'll show you in a moment, I think it's defined to be the same as null, or nil. To check whether it's a null stream? Yeah. You have to define it. Yeah. You have to define it. Okay? Yes?
What if you use a list of symbols and then bring it back? Like list prime A, prime B, then you can take the count and then put it back. So is that lazy or something?
Yeah, good point. Good point. That's a form of lazy evaluation, right? When you manipulate a list of symbols, it just so happens the symbols kind of look like a program, right? Yeah, that itself is a form of lazy evaluation. But that one, you have to construct it explicitly, you see. Here with you have to be careful what symbols to const together so that it's a valid expression, which is kind of a pain, right? Well, you do it once or twice is okay. It's kind of very good for exam questions, hint, hint. But really, when you want to do more elaborate lazy evaluation, you want sort of primitive support for those delay and force stuff, right? Okay? Good question. Other questions? No? So far, so good, huh? Okay. You guys are smart. That's why there's no questions. Okay? But we'll see some stuff that will stretch your brain a little bit. All right, so now let's see what happens when we do this. Okay? This is the same as before. It looks the same anyway, right? The idea here is you enumerate, you want to find the second largest prime, second smallest prime, sorry. Second smallest prime in the interval 10,000 to 1 million. The expression looks the same. It looks like you're going to enumerate everything first, then filter it, and then take the critter and take the car. Okay? But now, because of all these delay and force, things are not what they seem. Okay? Okay? We saw that, right? With the usual regular list processing, it's actually very wasteful. There's a lot of computation that goes to waste. Okay? But now with streams, we only need to compute. So here, I'll try and sketch the thing for you to convince you that this is actually more efficient. Clear? It's a bit hard to... Okay. So there's stream map, there's stream ref, stream map, filter. Stream enumerate interval is the same as before, okay? Although it's not defined here. Basically, you're just enumerating... Did you have a question? Yeah. Constream. Constream, Dr. Racket, in Dr. Racket, it's not a primitive. You have to define it. Ben Leong has provided some code for that, and I can get that available to you on IBLE. Right, so it's just a bunch of definitions that you have to load up front. Yeah, then you can click. Yeah. Yes, delay and force are primitives. Well, it depends on the scheme implementation, right? You see, Dr. Racket is one interpreter. When I was an undergrad, I used MIT scheme, right? That one is primitive. Yes? It has. Oh, stream dash cons, not constream, but stream dash cons. Okay, they kind of renamed it a bit, but it's a primitive. How do you choose that? What language? Or? Oh, okay. Okay, so there you go. Can you post that in the forum so that the rest of your classmates know? Thank you very much. So there you go. So there is. Okay, there is. You see, that's the problem. It varies from interpreter to interpreter. Okay? All right, so let me try and walk you through this. Now, when you, and for that I need like, let's look at the first one. Stream enumerate interval 10,000 to 1 million. So we're going to do stream enum interval, right? 10,000 and 1 million. I hope you can see that. My pen is kind of fat. Yeah? I'll try and write bigger, okay? Try and write bigger, but I hope you get the idea. Now, we haven't seen the definition for this, at least not given the lecture slides. But if you do look it up, okay, essentially it's what you expect. You go back to your chapter 2, you have your regular enumerate interval. It's exactly the same. It's exactly the same.
It should give you a pair with 10,000 and stream enumerate.
Exactly.
10,001 to...
Thank you very much. Yeah. So this thing will actually give you, because of the delay, because we're using const stream, it's going to give you something like, it's going to give you a pair. It's going to give you a pair, right? Because ultimately it's a stream. It's built up using const stream, so it's a pair, okay? The first thing is 10,000. The second thing is the expression, or it's a promise. It's a promise, huh? It's, okay? That contains stream enum interval 10,001 and then 1 million. Right? Okay, so this is kind of wrapped up as this is a promise. That's what stream enum interval will return you. It will return you that structure. Clear? Okay? You can trace through that. But the whole idea is the second part is actually delay. Delay. Okay? So in other words, this computation will take place really fast, right? I mean, the moment you call this, this is it. Okay? Because it doesn't actually enumerate everything. It only enumerates the first number, 10,000. And then delays everything else. Okay? So that's the first step. Okay, so that's the result. Then to that, you pass to, what's the... sorry. Right, so that's the bottom one, stream enumerate interval. That gets fed to stream filter. Okay? Stream filter is defined here. Okay? So if you look at it, it's the same. Okay? It checks, is the stream null? Yes, return the empty string. Otherwise, check the predicate on the car. Okay? Call the predicate with the car of the stream. If that is true, then const stream the car of that and recursively filter the critter. Right? You're familiar with this part, right? It's regular filter. And then, if this predicate evaluates to false, then just filter the rest and throw out that first element. Okay? So let's see, apply this to that data structure that we just got. Okay? Let's work along with me and you get a better understanding. Okay. So we're going to filter. So filter will check, is this an empty stream? Well, no, right? No. So what's going to do, it's going to apply the predicate onto the car. In other words, it's going to test prime 10,000. Right? Because that's the car. Right? It's going to call this predicate, right? This procedure. Okay? Now, so assuming it does what it's supposed to do, what's the answer for this? False. 10,000 is not a prime, obviously. Okay? So this evaluates to false. Okay? And so what does filter do? Ignores this element and recursively filter the rest. Okay? Now, let's watch it. Yeah. Yeah, correct. So let's go back to this thing again. So this predicate is returning false. So now you're going to evaluate the bottom part. Clear? Which says stream filter, pred, stream coulter, stream. Okay? So it's going to call stream filter, call itself pred, stream coulter, stream. Now remember, in stream coulter you force, right? Remember the definition of stream coulter, you force. So that's what we're going to do now. Okay? So this will result in calling stream filter with the prime on the stream coulter of this thing. Okay? That's the part here, stream coulter, which is going to force this promise. Okay? So when you force this promise, then this thing, you're actually calling stream in numeric interval again. That is when it gets called the second time. Clear? When you first call stream in numeric interval, it returns you that pair. But the second part is delayed. So now in the middle of doing stream filter, then it calls stream. Do you see that difference? Okay? So now this part, this chunk gets forced. So what will this return? This one will return a new pair, whose first element is now 10,001, whose second element is this promise. Hey, I can zoom out. Okay? I just have to be careful not to write on this thing itself. Okay? So this one would be stream in numeric interval 10,002, right? And then 1 million. That's the next promise. Clear? Okay, so now this thing is passed to this stream filter. Okay? So it you can see what's happening. Stream filter is doing its work. Sort of halfway through, it's got to stop, and then stream in numeric interval gets called again. Then now stream filter can continue. When does stream filter stop? Let's see. So far it's not stopping yet, right? I mean, it paused to wait for stream in numeric interval to come back. But now let's go on. Let's go on. Just press on a bit more. So now stream filter is going to do this. You can see what's happening. It's going to check whether 10,001 is prime. Is it prime? Let's assume it is, okay? Otherwise we'll just keep going. Let's assume 10,001 is prime. I mean, it's odd, so it's a candidate. Okay? So now, assume, assume, I don't know. Assume. So let's just assume, I don't know. Assume that prime 10,001 evaluates to true. Okay? Let's just assume that. And let's figure out what's happening. So now this is true. Okay, this is true. This is stream filter. This part is true now. Then what happens? Now you construct a stream. Now you construct a stream. Okay? So you're going to construct a stream, and this is what. So you see where this is going? Exactly. So now you construct a stream. The first one is now 10,001, right? It's going to preserve that element that satisfied the predicate. Clear? And then now this part is the promise. What is the promise? The promise is stream filter. It's a recursive call to itself. Stream filter with prime and stream coulter stream and stream coulter of stream, which is No, not yet. Don't jump ahead. Just follow mechanically. If you jump ahead, you get into trouble. Because things are delayed. If you jump to enumerate interval, you're in fact forcing it. I'm just trying to follow the code here. I'm trying to follow the code here in this part, that's all. Okay? You have to be careful, yeah? So let's do this part. So, it says const stream, so I create that pair. The first element is the car of the stream car stream, which is 10,001, right? And then the second part, this part, is actually a promise. This whole expression, stream filter, pred, stream cutter, stream, is actually wrapped up. It's frozen. It's not even evaluated at this moment. Okay? Okay, so that's what we're going to get here. A pair with the first element 10,001. The second part is that exact expression frozen solid. Okay? Do you see any stream in numeric interval here? No. No, not at all. Okay? So this is what stream filter returns. That's when it stops. Yeah, implicitly in this symbol. This symbol will point to another pair, a pair. A pair. What is this pair? This pair is, let me just hear. Is this one, this guy. This guy here. No, stream is this whole thing. Yeah, do your usual environment revised substitution model, whatever you use in your chapter 1. Okay? Follow that. That still works. Did you use revised substitution model? Okay. So this STREAM, this symbol, is actually this data structure here. Okay? Including the 10,001. Okay? Everybody with me? Did I lose anyone? Did I lose anyone? No? Okay. So far, so good. Let's press on a little bit more to see the result. Okay. So this is the structure returned by... I need a new color. Okay. Yeah, so this thing is returned by stream filter. That thing. Okay? Did a lot of work, but now we are done with this. We're done with this stream filter, because that's what stream filter returns. Okay? Now you go to stream cutter, you see. Stream cutter gets this green thing, right? And what's it going to do? It's going to force the cutter part. Well, the cutter is this promise. Force it. Then it kickstarts stream filter again, right? Do you see that? Okay? And then things start to compute again. Okay? Stream filter will return another pair, right? And so forth, okay? So do you see what's happening? Do you see that enumeration of the numbers is actually interleaved with the other procedures that wait on it. That's a crucial difference. Right? Previously, if you just call regular enumerate interval, all the numbers will be enumerated first, then the whole structure is passed to filter. But here it's not the case, right? Here you enumerate one item, delay the rest, then you pass it to filter. Filter is going to work on like one or two items, return something, and delay the rest. Coda is going to force further evaluation, and so on and so forth. Do you see the interleaving? Okay? So that's why this is actually a lot more efficient. But keeping track of it is no joke. Okay, and there's a temptation like what you did to immediately say, oh, it's going to call stream enumerate interval. Not yet. It's been delayed. It's been delayed. It will be called eventually, but not where you think it was. Okay, so you have to be patient and follow along. Use your revised substitution model. Just plug in and just be very careful and you get things right. Okay? Cool? All right, good. Yes, question? Which part? This part here? Instead of stream filter, what will you get? This part here. Oh, if you type in here const stream something, then what do you think?
I think it should evaluate to the first const.
Yes, it will. Because why? But at this moment, this whole chunk is frozen, huh?
My question is it frozen because you gave it the stream filter or?
No, it's frozen because this is the result. This green thing is the result returned by stream filter, which embeds a recursive call to itself. This green thing is what stream filter returns. Right? The first item is 10,001. The second item is a promise, which hidden in it is the recursive call to itself. It's kind of...
So that's what you put in the part of...
Yeah.
It will always be in the form of a...
Yeah. No, this whole chunk is a promise here. In the recursive call, it's not that this part is frozen. This whole expression is frozen. Okay? Clear? Now, eventually, if you force this, then that's just like a new procedure called to stream filter. Then stream filter will evaluate its argument. Stream filter is a regular procedure, so it will do the usual thing. It will evaluate all the arguments first. Right? So assuming you're calling stream filter, and this part was a const stream, then const stream will do its work and return you a new stream. The first part is force, the second part is delay. I wouldn't say one level. It forces whatever expression there is. If the expression causes another force, you could do this. You could always do this. You could always say force. Sorry, you could say this. You could say define X to be force Y. Delay force Y. Right? Suppose you say define X to be delay force Y. Okay? X will be a promise because of the delay. Right? So X will point to something that looks like this. This whole expression here is frozen. Okay? So now, if you say force X, right, then this thing gets unfrozen and evaluated, at which time you are well, the expression says force y now. So then you're forcing two levels in that sense, right? It really depends on your expression. You see the point? Okay? All right. I'm getting confused. You see my pen? My pen has two heads. Here, and I'm missing, and I know, clumsy me, I'm going to just stick it into my shirt, and then I'll look like Mr. Bean. I mean, whatever. Anyway, okay, so maybe it's time to take a break, yeah? Okay, let's take a 5 minutes break because we still have a bit to cover. All right, let's take a 5 minute break. And I'm supposed to play some video while you're having a break. Hey, you rather me play a video or want me to sing and dance, right? Okay, you just, no, thank you. No, thank you. You're not going to force me to do that. Sorry. Hello, this is not playing. Oh, I'm sorry. This is... Oh, there's no volume here. Can you hear? Oh, shucks. There is an audio cable which is plugged in. But there's no audio here. Hang on here.
This is really a 2-hour presentation.
Let me start again. All right.
This is really a 2-hour presentation I did to high school students, cut down to 3 minutes. We all started one day on a plane in the rate of 10, 7 years ago. And in the seat next to me was a high school student, a teenager, and she came from a really poor family. And she wanted to make something of her life. And she asked me a simple little question. She said, what leads to success? And I felt really badly because I couldn't give her a good answer. So I get off the plane and I come to class. And I think, geez, we're in the middle of a room with successful people. So I want to ask them what helped them succeed and pass it on to kids. So here we are, 7 years, 500 interviews later, and I'm going to tell you what really leads to success and makes Tedsters tick. And the first thing is passion. Freeman Thomas says, I'm driven by my passion. Tedsters do it for love, they don't do it for money. Carol Peretta says, I would pay someone to do what I do. The interesting thing is, if you do it for love, the money comes anyway. Work. Rupert Murdoch said to me, it's all hard work. Nothing comes easily, but I have a lot of fun. Did he say fun, Rupert? Yes. Tedsters do have fun working, and they work hard. I figured they're not workaholics, they work at frolics. Good. Alice Garden says, to be successful, put your nose down in something and get damn good at it. There's no magic, it's practice, practice, practice. And it's focus. Norman Jewison said to me, I think it all has to do with focusing yourself on one thing. And push. David Gallo says, push yourself. Physically and mentally, you've got to push, push, push. You've got to push through shyness and self-doubt. David Allen says, I always had self-doubts. I wasn't good enough, I wasn't smart enough, I didn't think I'd make it. Now, it's not always easy to push yourself, and that's why they invented numbers. Thank you. Thank you, he said to me, my mother pushed me. Serve. Shirley Newman says it was a privilege to serve as a doctor. And a lot of kids tell me they want to be millionaires. And the first thing I say to them is, okay, well, you can't serve yourself. You got to serve others something of value, because that's the way people really get rich. Ideas. Tedster Bill Gates says, we had an idea. Founding the first microcomputer software company. I'd say it was a pretty good idea. And there's no magic to creativity and coming up with ideas. It's just doing some very simple things. And I give lots of evidence. Persist. Joe Crank says persistence is the number one reason for our success. You got to persist through failure. You got to persist through crap, which of course means criticism, rejection, assholes, and pressure. So the answer to this question is simple. Pay $4,000 and come to play. Or failing that, do the 8 things, and trust me, these are the big 8 things that lead to success. Thank you, Ted Bruce, for all your involvement. Taking 12.
It's 8 minutes long and we don't have time for that, sorry. What's this supposed to be anyway? I see. Oh, the robot, I see. All the 10,001 users of the shovel. Oh, China shovel. I see. You have to be a soldier as well. Yeah, I'm sorry, I have to stop this because I saw. Yeah. Okay. Maybe you post it on forum or something. I don't know. Ben may say, may just scold me for encouraging interesting stuff. All right. But thanks for sharing that. Oh, is my voice back? Yeah? You can hear me. Hello. All right. So, okay, so I hope that gave you an idea of what we're dealing with now. Okay? This effect of delaying and forcing and how that actually makes computation more efficient. Okay? We're going to see a lot more. And we're going to see something that is really cool, something called infinity. Okay? I won't answer this question, maybe it's a bit philosophical, but as far as data structure is concerned, all the data structures we've seen so far are finite in that sense. Okay? Your lists have finite length. Have you done tables or trees? They're all finite. So now we're going to see a truly infinite length data structure. Infinite length. Okay? Okay, take a look at this. Okay? Define integers starting from n to be constraint n, and then integers starting from n plus 1 plus n1. Ooh. Okay? And now you define integers as integers starting from 1. Okay? So can you see that this is truly an infinite stream? And the reason you can do that is because of the delay. Right? Look at this thing. When you call, when you invoke this, when you say define integers starting from 1, this calls with n into 1, and then that calls constream 1 and something. So constream immediately returns you a pair whose first item is 1, whose second item is a promise. The promise to evaluate this thing, integers starting from 2. Wow, be careful. Integers starting from plus n1. That's the exact expression that's frozen. I'm not even going to replace plus n1 by 2 because that's not happening at that time. Let's be careful about that. Otherwise, it leads to, you may think that you're forcing more than is necessary. Okay? So the first constream, let me repeat. Constream returns a pair whose first element is 1, because n here is bound to 1, and this n gets evaluated to 1. Okay? Remember, the first argument to constream gets evaluated. So the n gets evaluated to 1. Okay? The second thing to constream gets completely frozen. The expression is frozen as is. So including the plus n1 here, that plus n1 expression is still there. It's not evaluated to 2 at all. Okay? So please be careful. When you freeze something, freeze it as is. Don't try and go in and say, freeze a little bit, but let me go ahead and evaluate this for efficiency. You'll get yourself confused. Okay? Okay? Behave like a machine when you're evaluating this, and you will not go wrong. Okay? All right. So that's how you can get infinite streams, right? All right. We'll see a few more. Okay? So this is really the infinite streams of all positive integers starting from 1. How about the following? Divisible xy equals remainder xy 0. You saw that. No force. What is no force? Stream filter. Lambda x not divisible x4 on the stream of integers. Infinite stream of? Yeah, things that are not divisible by 4. Okay? It's as if you read this purely in terms of Oh, where's my mouse? If you read this in terms of your chapter 2 knowledge, you already get the answer. If this were regular list and not streams, you will get that answer. It's a list of things, okay? But now you actually have an infinite stream, which you could never have in chapter 2. Agreed? Okay? Alright. So, I'll tell you what this procedure does, okay? This eval stream Sn, it's sort of like printing the stream, okay? In your textbook, you will see display stream or print stream. The problem is that the definition given in your book will not stop if the stream is infinite. It will just keep. So this one just says print or display n plus 1 element. Where's my mouse? Alright, doesn't matter. You can answer this question yourself. What is S? Is a finite stream with fewer than element. That's fine. No problem. Okay. What's the output? 5. Why 5? No fourth is a list of integers not divisible by 4. And you're asking stream ref 3, which is actually the 4th element, right? Remember, you start counting from 0. So it'll be 1, 2, 3, 5, huh? Because 4 is divisible by 4, obviously. So therefore the answer is 5. Yep. Okay, this one? Doesn't matter. So whatever. Okay? I'm not testing your mathematics here. Clear? Okay? I mean, it works as per normal. Now, if you do eval stream no force 10, then you're displaying the first 11th element, which is that. I mean, display them as a list. Okay, so the purpose of eval stream is just for display purposes, okay? Because otherwise the stream you see is dotted pair notation that gets very crazy.
If you want to get a list out of it.
Well, the purpose of, the way this is defined is for visualization purpose.
No, you get a actual list.
Yeah, exactly. So that
You can use it to manipulate something.
You could.
You want a part of the list. So.
Yeah, you could. That's fine. Yeah, true. It's a list. Alright, so let's see how we can play around and create infinite streams. So suppose you want to create the following stream, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. In other words, 1, 2, 3 repeated indefinitely. Okay, here's how you could do it. Define 1, 2, 3 stream as const 1, const stream 1, const stream 2, right? Const stream 3, obviously, you need the 1, 2, 3 to start off. And then what's the last part? Okay? So this is a recursive definition, obviously. But the reason it works is that because of the delay. Here, 1, 2, 3 stream is not evaluated right now. In fact, this const stream is not evaluated right now either. Neither is this const stream. Right? Only the first const stream is evaluated. That gives you a pair whose first element is 1, whose second element is the promise with this entire expression embedded inside. Yeah? Okay? You see that? Okay? So here's another example. Suppose you want to do this. Okay, so here's what the stream looks like. You start with 1, then you go 1 to 2, then you go 1 to 3, then you go 1 to 3, 4, 1 to 3, 4, 5, and so forth. Okay, so there is a pattern, but the pattern itself is growing, right? You see the thing? Okay, so here's how you might do it. You first define a helper stream A, B. You can study on your own, but the stream that you produce is called a growing stream, and you say helper stream 1, 1. Helper stream 1, 1. That calls helper stream here with A1 and B1. Now, when you call helper stream, it's a regular procedure, right? So you have to execute it, right? This is still eager evaluation going on here. So you say, is A greater than B? No, because A and B are both 1. So you fall to this part, which is a const stream. So now you create a stream, a pair whose first element is A, which is evaluated to 1, and whose second thing is this entire expression, helper stream plus A1B, frozen, wrapped up in a promise. And that's the result. That's what growing stream will point to initially. Is that clear? Okay, it's just one pair. One pair with the first element 1, the second element is a promise. That's what growing stream is. Okay, clear? Then it's only when you start to force stuff, like when you call eval stream, that forces the evaluation. Okay? Alright? Right. So here's the question of the day. I guess Ben likes games. He's asking you to play this game. Don't do it right now. Have some fun with it. Now, hint. Streams are very good material for exam questions. So it put some effort into understanding it, okay? Because I guarantee you, well, I can't guarantee. Ben is setting the exam questions. I haven't seen them yet. I don't think I want to see them, but Ben has been fond of giving you questions on stream. Okay, so put some effort to it. Okay, so stream processing is like list processing we saw, okay? Same thing, right? It's basically Const-K-Köder. When you use all these things, you use it as if they were lists. But because of the delay, lazy evaluation, you can actually do amazing things, right? So here's something that you could do. Write a procedure, replace, that creates a new stream with a specified target value, replace with another value. So for instance, replace growing stream 1 with the symbol A. Then, you remember growing stream? Growing stream is 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. Okay, replace all the ones with the symbol A. Okay, so you're supposed to come up with this. This is the answer. So interesting, huh? Replace string immediately returns you a const stream. Already. Whose first part, the first part is this if. So that gets evaluated. Huh? Remember, the first argument to const stream gets evaluated. It's the second argument that gets delayed. Clear? Right? So const stream will evaluate the first argument, which checks if the car of str is the same as A. Now, growing stream, if you call growing stream, the first symbol is 1, right? Which is equal to A. Then, therefore, you replace with B. So the const stream here, the first element is therefore the result of B, which is what? The symbol A. The second part of this const stream is this expression, replace blah blah blah, which is frozen. Okay? But that's the whole idea, right? You want me to replace a symbol? Well, I'll just replace the first symbol that I see. Or not. Right? Just handle the first symbol in the stream. And I delay all the work later. The rest of the work later. Okay? Okay? Alright, so another question of the day. Suppose you're given an arbitrary list L, where L is some A, B, C, D, E. Write a procedure generate stream that takes L as the argument and generates the stream. In other words, repeat L indefinitely. Okay? So you can do that. You can do that, of course. Alright. So here's we're dealing with prime numbers, okay? So here, this is an old method, but now made possible with modern computers. I love that. Okay? The sieve of Eratosthenes. Okay? It's a method to generate prime numbers. So here's the idea. You start with a list of all the integers, starting from 2. I mean, you don't care about 1. So you write down 2, 3, 4, 5, 6, so forth. Now, 2 is the first prime number. Agreed? Okay? So you keep that and you cross in your list discard everything that's a multiple of 2, because those can't be prime. Right? So now in this new list, with the even numbers crossed out, the next number after 2 must be prime. Because if it were not prime, you would have crossed it out. That next number happens to be 3. So now you cross out all multiples of 3. Of course, some are also multiple of 2, like 6, so you already crossed them out. But whatever is left, cross that out. So the next number remaining must be a prime, because otherwise you would have crossed it out, right? And that is 5. Then you cross out all multiples of 5 and so on. You get the idea? This is called the sieve of Eratosthenes. And here's the definition. Okay? So define sieve stream to be constream of the car of the stream. So keep the first element of that stream. Okay? Now recursively sieve the stream, but now you filter. Filter not divisible x by the car of the stream. So you take the first element, remember, for example, 2. You take 2 and you cross out all multiples of 2. In other words, you retain those that are not divisible by 2. That's the filtering part. Right? You retain those that are not divisible by 2. In this case, the first element of. Okay? Clear? Okay? So now you apply this filter with this predicate onto the curder of the stream. So you, Okay, take a moment to study this. It's a bit. Okay, this does what I just described, right? You take the integer starting from 2, keep 2, cross out all multiples of 2. In other words, retain those that are not divisible by 2. Filter that. And now recursively stream that. Okay? So this gives you a list of primes. Okay? So in terms of a diagram, what they call signal processing view, you can think of it like that. Here is the stream coming in. That stream gets broken up by car and curder into 2 parts, right? The car and the curder, obviously. The car is retained, right? That makes it back to the new stream formed by the con. But you also use the car to filter the rest of that stream, to retain those that are not divisible by the car. That's this box here. Okay? Right? After you filter that, what do you do? Well, sieve it again. It's your classic recursive thing, right? Okay? And once you have that stream, the result of that, you const back the first element to that, and you get back you get the final result. Okay? Questions, comments? Nope. Chugging along, okay. These are the other functions procedures that you saw. So once you have primes, you can just ask for the 51st prime, like that. Stream ret primes 50. Now, warning, when you invoke this, it may take a while, yeah? I mean, there's no magic. You are delaying the computation, but you're not speeding it up. When you finally have to do it, you have to spend the amount of time required to do it. Is that clear? Okay, so if whatever your delay is big O of n cubed, you will pay the price at that time, right? It's not going to take an n cubed and make it log n or anything magical. You're just delaying it, that's all. Okay, so when you evaluate that, oh, it's so slow now. Wow, it was fast when you created it. Okay, so there's no magic in that, all right? In other words, n cubed algorithm, if you delay it, will still run in n cube time. You're just running it later, but it will still take the same amount of time. Okay, there's no magic to that. Okay, you can go on and ask for the 500th prime number. I haven't tried, but you may have to leave it overnight. I don't know. All right. So more streams. Okay. So you saw add list or something equivalent in chapter 2, right? Where you take two lists and you add up corresponding elements. Well, you can do that for streams, so-called add stream, and here's it's very straightforward. To add S1 and S2, check if S1 is null, if so, it's just S2. Otherwise, create a new stream whose first element is the sum of the cars of both S1 and S2, and then recursively add streams for the CUDA. Well, if you're dealing with infinite streams, then the first check is redundant. The code is not complete. I'm sorry, there's one more here. Okay, thank you. Yeah, there's this funny check on S1, whether it's null. It makes no assumption. It just checks. S2 could be null the same time as 1 is null. That's entirely possible. But this one is more dealing with finite streams. If you have an infinite stream, the stream null will never be true.
But if S2 is shorter, then it won't be able to run.
Yeah, you get an error, yeah, obviously. Yeah. It's a funny thing. If you're dealing with infinite streams, in fact, this code is not very well written, right? Why are you assuming S1 is shorter than S2? What happens if, you can ask all kinds of questions. But so ignore that part. I don't like that part. It makes me... Okay. But the whole point is the bottom part, right? Which is, that's what it's supposed to do. All right. So, now let's use add stream. What is this stream? Define foo, constream 0, constream 1, add stream, stream CUDA foo to foo. Take a moment. It's going to hit you. It's going to hit you. You've seen it in chapter 1. You've seen it in chapter 2. Anybody guess? Yes? Fibonacci numbers, magical, wonderful, wonderful. Thank you, applause. Yeah, it's Fibonacci. You start with 0 and 1. I'll show you the diagram. Here it is. You start with 0 and 1 here. That's the constream 0, constream 1. That gives you the first two elements. Right? Then you add itself, which is 0, 1, and the rest you haven't seen yet because it's delayed, to the CUDA of that. And the result is you get Fibonacci. It's a bit weird. Huh? One slide back. Stream CUDA of foo to foo. Okay, you're adding the two streams. The first stream is, one of them is foo itself, the other one is the shifted, not shifted, but the tail part. Yeah? Okay. Okay? Okay? cs1101 is all about Fibonacci. That's what Ben says. Actually, I would say that cs1101s is about pattern recognition. You look at these things, oh, I know this pattern. Oh, it's a stream, or it's a Fibonacci, or Lucas numbers, or whatever. Power of Hanoi. Okay? You become very good at pattern spotting. Okay? The rest of the world out there, you tell them, what is 2, 4, 6, 8, 10? They say, oh, even numbers. Right? But you tell them what is 0, 1, 1, 2, 3, 5. You guys, Fibonacci numbers. So you have a larger vocabulary of patterns. All right, so here's another definition of integers. let's begin by defining ones. Define ones, constream 1 to 1. What do you think this gives you? Yeah, it's the infinite stream of ones, right? How about this one? Define integers, constream 1 to add streams, ones, which you just defined above, to itself. So, I really encourage you, go home and try it out to understand this, okay? Be careful. You will get it. You will get it. Okay? It's not that hard, but just have to be careful. Okay? This will give you, it's another definition for integers. Okay? But this one calls add streams to do it. Okay? Here's another one for Fibonacci, believe it or not. This is you can't count, right? You saw the very first recursive one in chapter 1, the iterative one, the log n version, right? Have you seen the matrix version? You've seen the memoized version. Have you seen the matrix version? You have, okay. Yeah. You've seen all kinds of ways to calculate Fibonacci numbers. So congratulations, you guys are expert at Fibonacci. You know, if you go to Science Center, Singapore Science Center, I just discovered it because I took my son there. On the floor outside the main building, there are these, I don't know, they're triangles or rectangles, you know, something. And the Fibonacci numbers are there on the ground. You know, and the size of the tile is proportionate to the Fibonacci number. So 1 is a smaller tile, then 2 is a little bit bigger, then 3, 5, 8. Of course, they run out of space very quickly, right? Okay. So that's how I first introduced my son to Fibonacci numbers, just by walking around. You know, and he was surprised that I knew the next number because he was very young there. He thought he knows 2, 4, 6, 8, 10. Then he says 1, 2, 3, 5. Then wait a minute, what's into 4? 5, then 8, what's into 6 and 7? Then I told him 8, 13, 20. Then he said, whoa, you're cool, Dad. Well, what do you know? I mean, I took 1101s, so next time you impress your own kid, okay? Alrighty. Okay, I think I have to end soon, right? Am I right? Yeah, because of the U-Town thing. Usually, I usually teach a night class. And I don't want to bother about releasing ahead of time because I don't. Alright. So anyway, so you can use streams for iteration. Okay, remember the square root procedure in chapter 1, right? Where you make a guess and you improve the guess. Right? And improving the guess, just calculating the average, right? That improves the guess. So here's this is what you saw in chapter 1. Now we can make it a stream version. Okay, define square root stream x to be define guesses. You're going to return guesses, but guesses is defined as constream 1. You always start with the first guess is always 1. Then you map, okay, onto itself guesses, recursive definition. This thing, lambda guess square root improved guess x. So you can do that. You just create the first element of the stream. Then the rest of it, you map the improved procedure onto the rest. Okay, this will work. So you notice this actually, in other words, as you go down the stream, you are getting more and more accurate values of the square root, right? In other words, you're replacing iteration with a stream. As you walk down the stream, it's as if you're doing the iteration. Yes. You try it. Why don't you try it? Remember the memoization we talked about earlier? What do you think? No, there was the delay could be memoized. No. It's already provided free of charge by the interpreter. Okay, you don't have to explicitly memorize it. But that's provided this is that's assuming the interpreter does the memorization. It may or may not, right? For Dr. Rackett, I think it does. I'll show you the code. So here's what you get, right? Let's look at the first 7 elements of this square root stream 2. Well, you start with 1, no surprises. That's your first thing. Then it goes to 1.5, 1.4, and this is how it... Okay, so you get more and more accurate guesses as you walk down the street. Clear? Cool, huh? So you've seen recursive version, iterative version, now the stream version. Very nice. Okay, then running along. Let's do pi, okay, and we'll end with pi. That's the other things. 101 is all about pi. Okay, so pi, as you saw in chapter 1, can be approximated by this infinite sum. Okay, but you notice the terms are alternating in sign, right? Minus 1/3, plus 1/5, and so forth. Okay, so let's define this. So you do pi summons of n, const stream 1 over n, and stream map the negative, because you have to flip the sign. That's what the stream map, this minus is for. It's to change the plus to a minus. Okay, map it onto pi summons recursive call with plus n2. Because you go from 1, 3, 5, 7, remember? That's how the plus n2 comes about. Okay? Then pi stream is scale stream partial sums, pi summons 1, 4. What is scale stream? Scale stream takes a stream and a constant, in this case 4, and multiplies every element of the stream by that constant. Yeah, it can be defined in terms of map. Yeah, map times 4. Okay, partial sums, you're supposed to define it yourself, but it's supposed to add up parts of the street, In other words, you say partial sum of this thing. This is a series. If I take the first partial sum, that will just be 1. I take the first term. The second partial sum will be 1 minus 1/3. The third partial sum is 1 minus 1/3 plus 1/5, and so forth. These are called partial sums. Okay? So that's what it does, and then here's the result. Looks pretty bad, huh? I don't see pi coming out anywhere. It's pretty far off. Have you seen a cartoon in the old Stone Age? Very cute. Stone Age, the value of pi is 4, because they draw a square. Right? Pi is circumference over diameter. So if you draw a square, the value of pi is 4, right? Obviously. Because in those days you couldn't draw a circle. Alright, so we start with 4. Alright, so here's the thing. Okay, you can read this, define scale stream and partial sum. But you see, the good thing about streams is that we could take this stream and accelerate it, speed it up. And here's how you do it. You use something called a Euler accelerator. For every term, this is discovered by mathematicians. For every term in your original series, replace it by Tn. For every term Sn in the original, replace it by Tn, where Tn is calculated by this formula. Don't ask me why. Okay, it's proven by somebody. And the new sequence, starting with consisting of your t's, will be faster version. In other words, it will converge to pi quicker. Okay, that's the idea. Okay, so it's just apply a mathematical trick. So you can do the Euler Transform S. Okay, you get the m plus minus 1, n and n plus 1 here. Virus scan. And then you constream. You apply that formula basically. This formula is just in here. And then you do it on the first element, and then recursively call yourself for the rest. But you delay that part. Okay? So now if you do that, if you take your original pi stream and you Euler transform it, now you see that it converges faster. It converges faster. Looks a bit more like pi now, right? Okay? Now you can keep doing this. 101 is all about recursion. So you take that, you accelerate once, now recursively accelerate again and again, okay? That's the cool thing. So here's what we're going to do. Okay, we're going to construct something called a tableau, which is this table. Tableau is a visual representation. Tableau is French, yeah? I think. Okay, where you take the first stream, the first row, S00, S01, and then from that you accelerate to get the second row, then you accelerate to get the third row and the fourth row and so forth. You keep doing that. So finally what you want to do, your final accelerated sequence is the diagonal, S00, S10, S20. Those are the super accelerated sequence. Okay? You know what I mean? Okay? So you can read up the details here, but look at this. Look at this phenomenal convergence to pi. This is up to like 13, 14 decimal places already, after just 8 iterations, well, so-called 8 iterations. Okay? And the reason you can do that is because you manipulate the stream at one go. You generate the first stream, yeah, then you just accelerate that and again and again and again. Okay? So that's the idea. So now your turn to do this on log of 2. And okay, so we're done basically. Alright? So you can think of, so that's the power of being lazy. I hope you are convinced that you can do amazing things with lazy evaluation. Yeah? Okay, remember your mom asks you to tidy up your room, say, yeah, mom, done. Okay? Then you don't actually do it. Then when she barges into the room, they say, okay. That's lazy evaluation. Okay, any questions, comments? No? Okay. It's very good exam material. Oh, here's one even more evil. If you combine mutation with streams. Okay? You can imagine that in streams, things are delayed, right? When you delay an expression, there could be some free variables, right? What if those variables are mutated? Oh, that's super evil, okay? Don't program like that. You drive yourself nuts. Okay? When you do streams, don't mix it with mutation because it's just all kinds of, you lose more hair, okay? Alright? But who knows, Ben may be very nice and give you a nice exam question that could, okay, I don't know. Alright, no questions. Thank you so much. I ran out of time, but see you on Friday. Friday we'll jump to Java. What? Java? No, you have several lectures on Java. The whole of next week is Java.